Hi, welcome to Materials Research Laboratory Scanning Electron Microscopy Orientation Seminar from University of Illinois at Urbana-Champaign. This orientation seminar is the first step of our SEM training. The presentation will be split into two parts. This is part one. There are three steps in our SEM training. The first step is this orientation seminar, a general introduction of SEM theory and operation. There are two videos. This is the first one. After you finish watching the orientation video, please go to the Compass 2G website to sign up for MRL SEM Orientation and take a short quiz. The second step is a group training on the instrument. In the group training, the operating procedure will be demonstrated step by step. All users in the group will get the opportunity to have hands-on for a few critical procedures, such as sample loading, microscope alignment, astigmatism correction, and image acquisition. The third step is an individual training on the instrument. You will bring your sample if it's available. SEM staff will sit with you and guide you to operate the microscope. The SEM staff will make sure you operate the microscope in the right way and may also help you to find the right set of parameters for your project. After the individual training, you may get daytime access to the microscope. Then you will need to finish a few self-use sessions, at least 10 hours on the instrument, before you can apply for full-time access to the microscope. Outline for the orientation seminar. This part, which is part one, will cover the first four topics. We will start with a general introduction of SEM. Then we will go over electron guns, electron lens aberration, and corrections. At the end, the beam parameters and their operator control will be discussed. The remaining topics will be covered in part two. First topic: what is SEM? Why do we want to use SEM? And how the SEM works. SEM is the abbreviation of scanning electron microscopy. It is a tool for observing and analyzing the surface microstructure of a bulk sample using a finely focused electron beam. The advantages of using SEM over optical microscopes include higher resolution. The resolution in SEM can reach nanometer range or even better. It has larger depth of focus and a wider range of magnifications. So what are the applications of SEM? The most common application of SEM is surface topography morphology study with secondary electron imaging. We can also get images with compositional contrast using backscattered electrons. We can even do composition analysis with energy dispersive X-ray spectroscopy EDS or wavelength dispersive X-ray spectroscopy WDS. Secondary electron imaging, backscattered electron imaging, and EDS. These three are the most common SEM applications, and they are available on most SEMs. However, with advanced analytical SEMs, we can also study crystallography with EBSD, which is electron backscattered diffraction, and also channeling techniques. We can even get optical or electronic properties with cathodoluminescence CL and electron beam induced current EBIC. As previously mentioned, SEM has much higher resolution than optical microscope. So what is the resolution in a microscope? Resolution is the ability to distinguish two very small and closely spaced objects as separate entities. As you can see from these two figures, on the left, the resolution is high enough to distinguish these two individual spots, although they are very closely spaced. On the right, the two spots are so close to each other that the central spots start to overlap. In this case, the resolution is not high enough to distinguish these two spots. In a perfect optical system, the resolution can be described by Abbe's equation. We can see that d, which is the minimum distance to distinguish, is directly proportional to lambda, which is the wavelength of light. Therefore, the smaller the wavelength, the smaller the d, the higher the resolution. In other words, in a perfect optical system, the resolution limit will be eventually set by the illumination wavelength. White light used in optical microscopes has wavelengths from 400 nanometer to 700 nanometers. So in order to further enhance the resolution, we need to go for smaller wavelength illumination, which is the reason electron microscope was developed. So the electron microscope was developed to enhance the resolution by using smaller illumination wavelengths. The electron wavelengths can be estimated by the equation here. We can see that the electron wavelength is inversely proportional to the square root of V, which is the electron accelerating voltage. Now we can have a rough idea about the electron wavelengths used in electron microscopes. At 5 kV, the wavelength is about 0.017 nanometer. At 30 kV, the wavelength is even smaller, 0.007 nanometer. In comparison, the wavelength of light used in optical microscope is between 400 nanometer to 700 nanometer. So clearly, by using electrons, the illumination wavelength has decreased by several orders of magnitude. The high resolution in electron microscopes is also owing to the high brightness source of electrons, as well as the electron optics, which allows the formation and manipulation of a very fine probe. The higher resolution and the larger depth of focus of SEM can be clearly observed in these two images of the same radiolarian. On the left, the image was taken in an optical microscope, and on the right, the image was taken in a SEM. We can see that in the optical image, only the top surface is in the focus, while both top and the bottom surface are in focus in the SEM image. And also, SEM image reveals extremely fine features which are not observable in the optical image. More examples of high depth of focus. In the left image are so-called rat's hair in a mineral sample, and in the right one is a carbon nanotube. The extremely large depth of focus in SEM is a very valuable feature for users, since it helps to create the impression of a 3D image of the feature. With an extremely wide range of magnification, SEM can show features with size ranging from several nanometers up to tens of millimeters. As you can see on the left image of a sensor device, the scale bar is 1 millimeter. On the right image, which shows gold platinum particles, the scale bar is 10 nanometer. So how the SEM works? First, An electron probe is formed by an electron optical system with GAN magnetic lens and apertures. The probe may be scanned across the surface of the sample in a rest pattern using scan coils. The incident electron will interact with the sample, generating various signals, and these signals may be detected by corresponding detectors, providing various information about the sample. The image acquisition in SEM is sequential. This animation shows you how it works. The probe is scanned in a rest pattern on the sample. The signals generated at each position are detected, converted into electrical signal, and then amplified, fed into display unit, where they are assembled to form an image. The pixel intensity on the display unit is made proportional to the signal received, therefore giving you an image contrast directly related to the area being scanned. One more animation on the sequential image formation of SEM. We can see that the magnification in SEM is actually the screen size over the raster size. While the screen size is fixed, when you increase magnification, what we are actually doing is controlling the scanning coil so that the scanning area becomes smaller. The general construction of SEM. First, we will need vacuum system. Electron sources beams require vacuum since an electron beam will scatter in a very short distance in the air. Second, we will need GAN so that electrons can be emitted and accelerated. Electron lenses. There are two types of lenses. The condenser lens sits right below the GAN. The function of condenser lens is to control the probe current and probe size. The objective lens sits right above the specimen. The function of objective lens is to make the probe focus on sample surface. Beam deflectors. In order to get good image, we will need the beam deflector to align the electron beam along the optical axis. And then, of course, we will also need the beam deflector to control the probe so that it will scan in the area we want. Objective aperture is to further demagnify the beam by blocking away the stray electrons and high-angle electrons. The specimen stage usually can move along 5 axes, x, y in plane, and z the height, tilt, and rotation. There are two types of detectors in SEM. Imaging detectors like secondary electron detector and backscatter detector. Analytical detector like characteristic X-ray detector, EDS detector. Finally, operating display system to control the microscope and display the data. Typical SEM operating conditions. Accelerating voltage, usually a few hundred volts up to 30 kV. Vacuum. The vacuum is not uniform inside the SEM. The highest vacuum is in the GAN area. It can reach close to 10 to minus 10 torr. The specimen chamber vacuum is lower, but will still be close to 10 to minus 5 torr in a conventional SEM. There is also a special type of SEM we call variable pressure or environmental SEM. This type of SEM can be operated under up to 20 torr. This type of SEM is very useful for in situ observation and measurements of samples which are not high vacuum compatible, as well as the uncoated non-conductive samples where charging is a problem. Various specimen stages such as cooling stage, heating stage, and the tensile stage are also available in some analytical SEMs. Now let's move to the second topic about the electron guns. There are three types of electron emission. The first one is thermionic emission, where electron emission is induced by heat. We can see that the potential barrier is not modified here. But with the help from thermal energy, the electrons are able to climb over the potential barrier to be emitted. The second is cold field emission, where electron emission is induced by electrostatic field. The electrostatic field applied is higher than 10 to 7 volts per centimeter. As a result, the potential barrier is lowered and becomes so thin that the electrons are able to tunnel through directly. The third type is Schottky emission, where electron emission is induced by heat, but also with the help of electrostatic field. The electrostatic field applied here is not as high as that in cold field emission, smaller than 10 to 7 volts per centimeter. But still, the potential barrier is significantly reduced as a result. Also, there is a zirconium oxide coated on the tip, which further reduces the potential barrier. Then, of course, there is a heating as well. So with the help from all these three resources, the electrons are able to climb the potential barrier very easily. Thermionic source. To make it easier for the electrons to climb over the potential barrier, thermionic source gun uses low work function materials, either tungsten or Lab6. They were made into the shape of a hairpin. We call them filament. Here is the construction of a thermionic gun. The heating supply. The walnut is negatively biased and used to focus electrons and control the amount of emission. And then anode, which of course is positively biased. It accelerates the emitted electrons. The filament emits electrons as a result of heating, according to Richardson's law. With the heating, temperature increases to a certain point, the electron emission current starts to increase, but eventually it will reach saturation. And usually we operate the gun at the onset of this saturation. Single crystal tungsten is used in the case of cold field gun. Along 310 direction, it is shaped into a sharp point so that the electrostatic field applied can be concentrated. The construction of a cold field gun. There are two anodes here. The first one applies ejection voltage on the tip, typically 3 to 5 kV. The second anode supplies accelerating voltage. In cold field gun, the tip surface needs to be atomically clean. Therefore, periodic flashing is needed to clean the tip surface. Schottky gun, also single crystal tungsten, shaped into a tip, but it is 100 oriented, and the tip is not as small as that in cold field gun. Also, there is a zirconium oxide coating on the tip to further reduce the potential barrier. The construction is similar to cold field gun, except a suppressor grid is added to eliminate unwanted thermionic emission from the regions outside the tip. Comparison of the three electron sources. Thermionic emission. The advantages of using thermionic emission gun. It has high probe current, which is good for analytical purpose. It has a stable probe current, especially for tungsten. And since the gun area does not require ultra-high vacuum, the vacuum system required is less complex, so the overall cost is lower. The disadvantages of thermionic emission gun. It has lower brightness, which is not good for ultra-high resolution imaging. Also, it gives less monochromatic electrons, which means the electrons emitted have a larger energy spread. So chromatic aberration is a significant issue in low voltage imaging. Cold field emission gun is kind of the opposite of the thermionic source gun. It has higher brightness, which is good for ultra-high resolution imaging, and the electrons emitted have a smaller energy spread, which means it gives more monochromatic electrons, and it is very good for low voltage imaging. However, the maximum probe current obtained in cold field emission gun is low, which is a disadvantage for analytical purpose since the signals will be too weak for a quick analysis like mapping. Also, it requires ultra-high vacuum in the gun area, therefore the overall cost is much higher. Schottky emission gun kind of combines the advantages from both thermionic gun and cold field gun. It has high brightness. It can also give high probe current. Characteristics of 3 electron sources. First, let's look at the critical ones discussed in the previous slides. Brightness. Tungsten is only 10 to 5 to 10 to 6 amps per square centimeter steradian. Lab 6 is slightly higher. Cold field emission reaches 10 to 9, about 3 orders of magnitude higher than that of thermionic source. Schottky is 10 to 8, very close to that of cold field emission gun. Energy spread. Tungsten is 1 eV, while cold field emission is only 0.3 eV. Maximum probe current. Tungsten is as high as over 1000 nanoamps, and the cold field is less than 2 nanoamps. Schottky can vary in a wide range from 10 nanoamps to 500 nanoamps. Spatial resolution might be one of the most important specifications of a microscope. Let's take a look. Resolution in SEMs with tungsten source is no better than 3 to 4 nanometer, while resolution in SEMs with cold field emission gun can reach 1 nanometer or even better. Schottky source SEM is again very close to that of SEM with cold field emission gun. Next topic is electron lens aberration, and corrections. While glass lenses are used in optical microscopes to focus light, electromagnetic lenses are used to focus electron beams in SEMs. Copper coil is wound around soft iron. The current applied through the coil produces a magnetic field. The small slit in the iron allows magnetic field to leak into the column. The focusing action of electrons follows Lorentz force equation. As mentioned previously, in a perfect optical system, the resolution limit is eventually set by the illumination wavelength. But there is no perfect optical system, so there are always other resolution limiting factors. For an ideal lens, beams that emitted from a point source will be focused to the same plane. So the point source is focused to a point. But ideal lens does not exist. In the actual lens, beams that emitted from a point source are not focused to the same plane. Therefore, a point source is focused to disks. We call these disks disk of confusion. The smallest disk obtained is called disk of least confusion. The effects which cause different beams to focus to different planes are called aberrations. They are aperture diffraction, spherical aberration, chromatic aberration, and astigmatism. These aberrations reduce resolution by limiting the achievable probe size. Spherical aberration and aperture diffraction. What is spherical aberration? High-angle beams are bent more strongly by the lens magnetic field than those beams near the axis. The disk of least confusion for spherical aberration is proportional to the cube of convergence angle alpha. Aperture diffraction. So wave nature of electrons will lead to a pattern instead of a point in Gaussian image plane. The disk of least confusion for aperture diffraction is inversely proportional to convergence angle alpha. Therefore, the spherical aberration and aperture diffraction varies in the opposite direction with alpha. So there is an optimum aperture angle, which is determined by combined effect of spherical aberration and aperture diffraction. As mentioned earlier, there is always energy spread in the electrons emitted from the source, which means the electrons emitted do not have exactly the same energy as set by the accelerating voltage. Chromatic aberration causes electrons emitted with different energies along the same beam path to be focused to different planes. As shown in this animation, the red beams focus at the plane which is much closer to the lens than the green beams and the blue beams. The disk of least confusion for chromatic aberration is determined by this equation. We can see that it is proportional to the energy spread delta E, but inversely proportional to E0, which is the beam energy set by the accelerating voltage. This means chromatic aberration increases with source energy spread delta E and decreases with increasing electron energy E0. Therefore, operating the microscope at higher accelerating voltages will help to reduce chromatic aberration. So how do we know there is astigmatism that needs to be corrected? First, regardless of how hard you try, the image cannot be focused, like the one shown here. Second, you will see feature stretching as you turn the focus knob through focus and defocus. The two stretching directions are perpendicular to each other. The reason behind the feature stretching is the shape of the probe changing from round to oval due to astigmatism. Astigmatism can be corrected by stigmators, which are sets of magnetostatic lens. Stigmator helps to bend the electron beams so that they focus at the same plane. Assume these are the electron source, and in order to get high resolution imaging, we want a small probe. That is, the source needs to be highly demagnified. Before astigmatism correction, depending on the objective lens focus, the probe shape changes from oval to round and to oval again. The point here is, even when the probe is round, the probe is still not highly demagnified as we would hope. After astigmatism correction, beams are made to focus at the same plane. Now, as you can see, this time the probe is being highly demagnified. Therefore, we will be able to get a clear image using this small probe. Here is the step-by-step procedure of astigmatism correction. First, focus the image in such a way that the stretching is minimized. The image will appear out of focus due to astigmatism, which is okay. Second, adjust the two stigmator knobs one by one to make the image as clear as possible. Then you will need to iterate until no more improvement is possible. Now let's move to the next topic, major electron beam parameters and their operator control. Major electron beam parameters. First, electron brightness of the probe. It is essentially equal to the brightness of the electron source. It is a very important parameter, but it's not something that an operator has control of. Probe diameter dp defines the size of the probe when it hits the sample surface. Probe current IP defines the amount of electrons arriving at the sample surface per unit time. Probe convergence angle. This is also a very important parameter, and it will be discussed later in the presentation. Accelerating voltage determines the energy the electrons carry when they hit the sample surface. These four parameters can be controlled by the operator. Actually, as an operator, you must optimize the probe conditions depending on your project needs. For example, if obtaining ultra-high resolution is the most important thing, then you need to use a smaller probe. Or if obtaining a high depth of focus is the most important thing, then you will need the probe to have a smaller convergence angle. Probe size and current are controlled by condenser lens. The function of condenser lens is demagnifying the electron source. By adjusting the lens current, we can make the lens weak or strong. If the condenser lens is weak, we are getting a longer focal length. As a result, the electron source is less demagnified. Therefore, the probe is bigger. The probe current obtained is also bigger since a smaller convergence angle leads to fewer electrons being blocked away by the objective aperture. Therefore, the image will have lower resolution but will be smoother due to a larger probe and a larger probe current. If the condenser lens is strong, we are getting a shorter focal length. In this case, the electron source is highly demagnified. Therefore, the probe obtained is smaller. The probe current is also smaller since a larger convergence angle leads to more electrons being blocked away by the objective aperture. So the image we are getting has higher resolution, but will be rougher due to a smaller probe and a smaller probe current. Before we get to the objective lens, let's first take a look at the concept of depth of focus. Depth of focus is the distance above and below the plane of focus that beam becomes broadened to a noticeable size, blurring the image. Depth of focus is inversely proportional to convergence angle alpha. For example, if we have another beam with a much larger convergence angle, we can see that the beam will get broadened much quickly, leading to a much smaller depth of focus. The depth of focus is also dependent on the magnification used. The higher the magnification, the smaller the depth of focus. Working distance is one of the most important concepts in SEM. Working distance is the distance between the bottom of the SEM column, which we also call the pole piece, and the sample surface. In order to obtain a clear image, the beams need to be exactly focused on the sample surface. If the beams focus below the sample surface, we call underfocus. If the beams focus above the sample surface, we call overfocus. Either way, the probe size is not minimized. Therefore, the image won't be clear. It is the objective lens which controls the focus, therefore directly controls the working distance and the depth of focus. We can make the objective lens stronger by increasing the lens current. Strong lens has a shorter focal length, which means a smaller working distance. Also, strong lens highly demagnifies the probe, so the probe hitting the sample will be smaller, which means a higher image resolution. A strong lens also makes the convergence angle bigger, which means a smaller depth of focus. We can make the objective lens weaker by reducing the lens current. Weak lens has a longer focal length, which means a longer working distance. Also, weak lens less demagnifies the probe, so the probe hitting the sample will be bigger, which means lower image resolution. A weak lens also makes the convergence angle smaller, which means a larger depth of focus. We can also get smaller probe size as well as smaller alpha by using a smaller objective aperture. This way we can get better resolution as well as better depth of focus. The end of part 1. Please watch part 2 to finish this orientation seminar.